This session discusses detriment and the application. And we invited 4 speakers and 1 reporter. And you may know the ICRP, the published publication 142, which is titled Radiation Detriment Calculation Methodology. Radiation detriment has been used in the determining and tissue weighting factor and a very important risk index and detriment. And publication 152 pointed out there is room for improvement in cancer risk model based on the latest epidemiological study, and also improving concept of the detriment in terms of the communication. Okay, today our session give you 4 presentations. 4 presentations discuss what is the latest information regarding LSS study, and how to estimate the risk when you apply to other population for radiation protection purpose, and which is a biological mechanism behind sex difference of lung cancer. And finally, what is a better risk indicator for improving communication? Okay, first of all, I would like to ask Jun Hirouchi to summarize a paper submitted in our session. Okay. Jun Hirouchi was worked for 8 years at Japan Atomic Energy Agency, JAA, researching those assessments for the public and effect of protective measures and related to level 3 probabilistic risk assessment. And he also researched those assessments to the environment in the UK Health Security Agency 2 years ago. Recently, he has been researching cancer risk assessment in terms of radiation protection. Jun Hirouchi, you have the floor. Please.
Thank you, Chair. I'm Jun Hirouchi from Japan Atomic Energy Agency. I will introduce summary of contributed poster and pre-recorded videos in session 16. So section 16 has 6 posters and 1 pre-recorded videos. So 4 posters from Japan and 1 poster from Nepal and 1 poster from Germany and 1 pre-recorded videos from Canada. So this table summarizes the authors' titles and keywords. So now let me summarize each topic. So first, Tetsuhiro Kinugawa et al. Presents the mathematical model for the occurrence of DSP, double-strand break, taking account of the repair of SSB, single-strand break. The authors constructed a mathematical model which expresses the occurrences and recoveries of DNA strand breaks. The model helps one to understand how the repair of SSBs influences the number of radiation-induced DSBs. So next, Tatsuki Kimura et al. Presents the application of disability-adjusted life years (DALYs) index for radiation and other risks, preliminary calculation results and considerations. This presentation will provide some preliminary results of quantitative estimation with DALY index of the occupational risk and cancer risk induced by radiation and chemical carcinogens as well as challenges in risk comparison. So Marcus Adamura presents aspects of risk projection models relevant for detriment calculation and application to radiation-induced leukemia. Challenging a leukemia model which show highly complex age and dose dependencies. Such models has been developed in projects for assessment of the assigned share for different leukemia groups, or ALL, CML, AML, and lymphoma. These models were refined to provide robust risk estimates for all possible ranges of occupational exposure. So Keisuke Hamada et al. Presents a probabilistic method for predicting acute radiation dermatitis grades in patients with head and neck cancer using a model based on Bayesian probability. The authors developed an acute radiation dermatitis ARD prediction method based on Bayesian probability. The model can predict ARD grades at the treatment planning stage. Baru Bikram Katori et al. Presents in situ radiometric assessment of rural region in Gurumi, Nepal. This study conducted to investigate the distribution of natural radiation and dose rates in the rural and Satyawati of Gurumi district along the Karigandaki River in Nepal. The average absorbed dose rate in air were 103.8 nanogram per hour to 118.2 nanogram per hour, and are higher than the world average value of 59 nanogram per hour. In addition, the average values of the external hazards index were 0.59 to 0.70 and are within the world recommended safety limits. And Takahiro Wada et al. Presents a mathematical modeling of alkene recovery. In this presentation, alkene recovery is investigated from the viewpoint of mathematical modeling. This presentation will show that this model can reproduce the essential features of alkene recovery, such as the reappearance of the shoulder in the survival curve, increase of the survival rate with the number of spirits, and increase of the recovery rate with the length of the non-irradiation period. So final pre-recorded video by Monima Martin et al. So presents a need for modified seabed as radiation dose unit. The authors suggest that a modified seabed which factor in physical and chemical properties of the nuclear and molecular constituents of the medium be introduced. This will not only guide medical practitioners, but will also allow the public and policy makers to discern medium-specific effects of diverse radiations, set protection protocols which are presently based on heavily extrapolated data, and help resolve the low-dose ambiguities related to LNT or non-LNT dilemmas. So all posters and pre-recorded videos are shown in website, so please access the website. That's all. Thank you.
Thank you very much. And I'd like to introduce an first invited speaker, Dr. Arina Brenner. She is working RF in Japan. And she is a member of TZ122, update of detriment calculation. And she is working on the analysis of our lifespan study for atomic bomb survivor. Arina Brenner, you have the floor, 15 minutes.
Good morning, everyone. It's my pleasure to be here and talk about analysis of all solid cancer incidents in the lifespan study cohort of atomic bomb survivors. I am giving this presentation on behalf of our working group that includes scientists from Japan and the United States. Sorry, how do I advance? As you know, there have been 3 comprehensive reports concerning cancer incidents in the lifespan study cohort. Unlike first 2 reports by Thompson and Preston, the most recent report for 1958-2009 follow-up consists of a series of papers shown on these slides with common methods. The advantage of this approach is that it facilitates comparison of risk across cancer sites and at the same time allows for more nuanced modeling of baseline rates and dose response. In all analyses, the follow-up was extended by 11 years through 2009. And with that, we added nearly 6,000 new cases of solid cancers to a total of over 22,000 cases. Importantly, 72% of new cases occurred among individuals who were less than 20 at the time of the bombing. We also applied improved weighted organ-specific radiation doses, primarily based on improved survival location and trace shielding data. As in the past, the doses were calculated using and assuming neutron RBE of 10 and corrected for those errors, assuming 35% coefficient of variation in individual dose estimates. We also updated estimates of migration rates and excluded cancer cases identified at autopsy only and not suspected clinically to minimize ascertainment bias due to early years of autopsy program at ABCC. Last but not least, for the first time in major incidence report, we used mail survey and clinic-based questionnaire data to adjust for relevant lifestyle factors depending on cancer site. Overall, the data were available for about 60% of LSS participants. Now, to characterize effects of radiation and lifestyle risk factors on rates of solid cancer incidence, we applied Poisson regression methods for group survival data, as in previous analysis of LSS data. And we fitted excess relative risk and excess absolute risk models of the following forms. Here, the first term, lambda 0, refers to baseline rates among unexposed survivors, or actually survivors with 0 doses. The second term refers to excess relative risk due to radiation, or excess absolute risk in this model. And the last term refers to the excess relative or excess absolute risk associated with lifestyle factors. The form of the model varied on type of cancer, and in this presentation, I will give you details for modeling of 3 outcomes: all solid cancer, lung cancer, and female breast cancer. Now, the baseline rates for all solid cancer were described and characterized in terms of sex-specific quadratic spline in log of attained age with a nut at age 70, as well as log linear trend in year of birth, and rates were allowed to vary for individuals in city and not in city at the time of the bombing. On this figure, you can see the fitted baseline rates among individuals exposed to zero dose and non-smokers in relation to attained age, shown for males and females and 3 different years of birth. Just very briefly, this is a typical pattern for many adult onset solid cancers. Rates quickly increasing, rapidly increasing between 50 and 70 years of age, flattening at older ages. The increase is faster among males than females for the same year of birth. And at the same time, for the same attained age, rates are higher among individuals born in more recent birth cohorts. I should add that this form of the model for the baseline is typical for many other sites that we analyzed. Some differences included how temporal changes in baseline were characterized. For some cancer sites, it was investigators opted for using calendar period effect rather than birth cohort effect, while for others, there was a need for additional allowance for potential screening effect due to AHS participation. Now, let's look at the form of radiation relative risk. I'm sorry. The radiation excess relative risk is a product of sex-specific dose response function, linear, quadratic, dependent on sites, and effect modification function with allowance for effect of attained age modeled as a power trend and aged exposure modeled as a log linear trend. In addition, in this report, allowance was made for individuals exposed to total shielded kerma above 4 gray to minimize the influence on estimation of dose response shape. Here, you can see the fitted dose response for males on the left, females on the right, at attained age 70, following exposure at age 30. As before, in LSS data, there is strong evidence of dose response with risk increasing with increasing dose both among males and females. However, the new finding is that the dose response for males was best described by a linear quadratic function rather than linear function that was shown in previous data. Still, there was no evidence of departure from linearity among females. One consequence of the curvature is, of course, that under linear quadratic model, in the low to moderate dose range, risk would be lower for males than those that are predicted by linear model. Now let's look at effect modification pattern. Here, as I said, it was allowed to depend on attained age and aged exposure. As in previous data, the excess relative risk for a given dose decreased strongly and significantly with increasing attained age for any aged exposure. The new finding is that the speed of decrease is faster among males than females, and therefore you can see the sex-specific indicators for the attained age effect. With respect to aged exposure, once cases identified at autopsy were excluded, then previously reported U-shaped pattern in aged exposure could be rejected statistically. And the data were well described by a log linear model in aged exposure with no evidence that it had to vary among males and females, unlike attained age. Now I'm going to talk about smoking excess relative risk and how it was included for adjustment purposes, and give you example of lung cancer for which modeling of smoking effect is essential. You can see from this expression that the model for smoking excess relative risk is quite complex. Very briefly, the effect of smoking is allowed to depend on cumulative smoking exposure, modeled as pack years smoke, with allowance for unknown smoking status, as well as independent effects of smoking intensity, modeled as cigarettes per day smoked, duration of smoking, smoking cessation, and year of birth. So there are many ways in this complex data could be visualized. This is one form of presenting, focusing on the effect modification by smoking intensity in this panel and smoking duration. So you can see that for the same number of pack years, let's say 50 pack years, smoker with a history of 50 pack years, the smoking excess relative risk is increasing as smoking duration increases. In contrast, the smoking risk is decreases as smoking intensity increasing. Now, to model joint effect of radiation and smoking on lung cancer rates, as in previous analysis by Furukawa and Pierce, Cahoon fitted 3 types of models. On the simple additive model, the effects of radiation and smoking are independent relative to baseline rates. On the simple multiplicative model, effect of radiation is assumed to be proportional to the effect of smoking. And on the generalized multiplicative model, neither is true, where excess relative risk with radiation is additionally allowed to vary by smoking intensity, and this was modeled as log linear quadratic trend. So I would like to say that for other cancers than lung cancer, we relied on simple multiplicative model to describe radiation and smoking effects, while for lung cancer, the data was best described by generalized multiplicative model. On this panel, you can see the lung cancer excess relative risk fitted due to radiation and smoking relative to unexposed non-smokers. And this was estimated under each of these models. The generalized multiplicative model fit is shown as solid black line. And the main message is that as smoking intensity is increasing up to approximately 10 cigarettes per day, the lung cancer risk is increasing, and then it's decreasing to essentially no radiation-associated risk for smokers of 20 cigarettes or more. Now, to the extent lung cancer is about modeling of smoking effect, female breast cancer is about modeling reproductive factors, both in baseline and in radiation excess relative risk. Here you can see expression that was equation used to model breast cancer radiation excess relative risk. The risk was strong and linearly related to dose. As before, risk varied by attained age, but the new findings were, and we allowed for the effects of menarche age and aged exposure. Aged exposure in previous female breast cancer data in LSS was modeled as log linear trend. Here we applied a different model which allowed the slopes in aged exposure differ before and after menarche. Let's look at fitted patterns by attained age, menarche age, and aged exposure. For breast cancer, radiation excess relative risk decreased with increasing attained age at speed similar to that for all solid cancer among females, for any menarche age. It also independently and strongly decreased with menarche age by estimated 24% per year increase in aged menarche. And for the same attained age and menarche age, the radiation excess risk depend on aged exposure in such way that as closer aged exposure gets to menarche age, risk is increasing, peaking at menarche age, and then decreasing slowly. I would like to add that similar pattern in aged exposure was also found for uterine corpus cancer. And if you need more details, please look publication by Utaga. It's very interesting similarity of the patterns for these two sites. Now, to summarize, some of the points I was not able to make during this presentation, but overall, collectively, the updated incidence effort continues to show that atomic bomb radiation exposure resulted in increased rates for almost all solid cancers among both males and females of all ages at exposure. Radiation excess cancer cases continue to occur more than 60 years after exposure, with many new cases, particularly among those exposed in childhood and adolescence, and improved methods provide more precise estimates of radiation risk as well as complex effect modification patterns. And with 73% of survivors who were exposed at below 20 years of age being alive as the end of 2009, and peak of excess cases that is expected in 2015-20, it's important to continue updating solid cancer incidence in LSS in order to refine understanding of the evolving dose response shape, patterns of radiation risk, and estimates of lifetime risk. In closing, I would like to acknowledge and thank all those who directly contributed to this work, and many are in this audience. And thank you for your attention. Thank you.
Thank you very much, Arina. Thank you very much for comprehensive summary and new information and atomic bomb survivor data. We are going to have a discussion, general discussion time after for speaker finished, and now is a very quick, very simple, specific, and burning question accepted. If you have question, please raise a hand. Okay? Okay. Shall we move on then? Okay. I'd like to introduce the next speaker. Dr. Rana Hafner is a physicist and holds a Master of Science in Physics from ETH Zurich. And since April 2020, she is working at the Swiss Federal Nuclear Safety Inspector, ANSI, in the section of the Occupational Radiation Protection. In October 2020, she started a doctorate at the medical faculty of the University of Munich, as well as an internship as a scientific secretary and the C1, ICRP C1 committee. Rune Hafner, you have the forward for 15 minutes. Thank you.
So thank you very much for the introduction. I'm going to present a short review of published multimodal inference studies in radiation epidemiology and some new developments. So first, I'm going to introduce you to multimodal inference, or shortly MMI. I'll give an overview of MMI publications published so far. I'll address some challenges with MMI, and then I'll talk about some new developments. So what is multimodal inference? So if we have a data set, we usually have several models that fit the data approximately equally well. So then if we choose one specific model for cancer risk calculation, this leads automatically to an uncertainty that comes along with the uncertainty of model choice. Now, can this uncertainty of model choice be assessed? Yes. With a statistics information theory-based technique for superimposing different models that could fit data almost as well as each other, called multimodal inference. So I'm going quickly through the MMI methodology. So assuming we have M models I, and we want to assess a risk Ui. So for each risk Ui, we need to calculate the archaic information criterion. This is a quantity that quantifies the goodness of fit of a model to the data. And this is calculated with the deviance, which is also a quantity that quantifies the goodness of fit of a model to the data, and 2 times the number of parameters of the model. Then for each risk Ui, we need to calculate the AIC-based weight, Wi, and this is done with this formula here. And then we form a weighted average of the risk, and we get the uncertainty. And this weighted average is then the model averaged risk estimate, which we get from MMI. And the uncertainty you can calculate with this formula given here. Alternatively, you can also assess the uncertainty via Monte Carlo simulation, or you can use the Bayesian information criterion instead of the archaic information criterion to calculate the weights. So what are the advantages of MMI? So MMI allows risk estimates to be based on several plausible dose-response models rather than just relying on one single model of choice, which is usually the LNT model. It also provides a more comprehensive characterization of model uncertainties by accounting for the bias from model selection. Further, the shape of the MMI-derived dose response is better characterized than the shape of any individual dose response because it accounts for the strength of evidence for each of the contributing dose responses. So there have been some publications in radiation epidemiology that were using MMI. The first one was from Walsh and Kaiser. It's called Multimodal Inference of Adult and Childhood Leukemia Excess Relative Risk based on the Japanese A-bomb survivors' mortality data from the 1950s to the 2000s. And they used 9 published leukemia excess relative risk models and calculated a model average excess relative risk with them. In this table, you can see the model references, the number of parameters of the models, the deviance, the AIC, and the calculated weights. And they came up with a model averaged excess relative risk at 1 sievert of 2.77 with a 95% confidence interval reaching from 1.43 to 3.84. It was calculated at an age at exposure of 30 and an attained age of 55. They then performed a follow-up study. It was an independent analysis of the radiation risk for leukemia in children and adults with mortality data from the 1950s to 2003 of the A-bomb survivors. And here they analyzed over 40 models, and then they did follow the model selection protocol. And in the end, they came up with 4 models that contributed to the MMI, where the best fitting model was the model with a purely quadratic dose response with an exponential damping factor at high doses. In this figure, you can see the excess relative risk as function of dose and the different dose response curve, or the different risk curves coming from the dose responses using here, as well as the curve from MMI. Kaiser et al. Did an analysis with breast cancer risk in A-bomb survivors with MMI, with incidence data, and they used combined risk from empirical and mechanistic two-stage colonial expansion models, where the later models relate the radiation risk to cell processes, which are controlled by age-increasing rates of initiating mutations and by changes in hormone levels due to menopause. And the later models were found to have an enhanced excess relative risk for an exposure at young age, which is can be observed in this figure. It was calculated at an age at exposure of 10 years, whereas the preferred empirical model here shows no dependence on age of exposure. So Schoenberger et al. Did a study called Dose Responses from MMI for Non-Cancer Disease Mortality of the Atomic Bomb Survivors, and they analyzed cerebrovascular and cardiovascular diseases. Therefore, various parametric and categorical models were analyzed with a statistical selection protocol that rated the model description of the data. So for cerebrovascular disease, they found with MMI a weak dose response below a step of 0.6 gray. It's like 1/3 of LNT, and above that step, the dose response was found to be higher. And for cardiovascular disease, a LNT type dose response was found with risk estimates consistent with 0 risk below 2.2 gray. Then a similar analysis followed from Schoenberger et al. They also analyzed those responses from mortality from cerebrovascular and heart diseases in the atomic bomb survivors. Here, radiobiologically motivated linear and nonlinear dose response models were used. And for heart diseases with MMI, a sublinear dose response was found compared to LNT, and for CVD, a sublinear dose response was found at low and medium doses, and MMI predicts a higher risk compared to LNT at higher doses. And the last study I want to address here is also from Schoenberger et al. It's called radiobiologically motivated modeling of radiation risk of mortality from ischemic heart diseases in the Canadian fluoroscopy study. Also here, radiobiologically motivated nonlinear dose response models were analyzed, and MMI indicated an essentially linear dose response at low and medium doses and a supralinear relationship at higher doses. So what are the challenges with the MMI approach? So first, there's the choice of the information criterion. So we have the Kaike information criterion and the Bayesian information criterion, and there's no clear best choice. And second, we have a panelization of models with stratified baselines. So excess relative risk models are either modeled with a parametric or a stratified baseline, And parametric baselines have much less parameters than stratified baselines. So stratified baselines models have a heavy disadvantage in MMI because they're just eliminated. But there have been some new developments regarding this point. Recently, a study was published from Stabilini et al. It's called Comparison and Multimodal Inference of Excess Risk Models for Radiation-Related Solid Cancer. Here, MMI was performed with recently published all solid cancer models. And here, the stratified baseline problem was addressed. So they fitted all the published all solid cancer models twice to the most recent LSS incidence data, so, which is publicly available. Once they fitted a total model, meaning the baseline and excess risk model to the data. And second, they fitted, like from all the published models, they were looking for the best fitting baseline, and then they altered just the excess absolute relative risk models. And so you could find a way around the stratified baseline problem. And also in this study, both weights were used, so AIC and BIC. The results are shown in this table. For AIC, for variable baseline, we see that the unscaled linear and linear quadratic model do dominate the model average and of the risk estimate. And for constant baseline, it's the Beer model and the Grant linear and linear quadratic model that dominate. If you use BIC weights, for the variable baseline, it's the Grant linear and linear quadratic model that dominate for absolute excess relative risk. And for the constant baseline, it's the Beer model, again, that dominates. So from this study, we get 8 different model averaged excess risk estimate. In a next study called Application of Multi-Method Multi-Model Inference to Radiation-Related Solid Cancer, Excess Risk Models for Astronaut Risk Assessment, these models were then implemented into a cumulative risk assessment method to see what the impact would be. So these were implemented to calculate the radiation-attributed decrease of survival. And here, risk estimates calculated with models based on AIC weights have been found to be smaller with narrower 95% confidence interval than risk estimates calculated with models based on BIC weights. Further, there has been a new approach introduced in this study. It's called Multi-Method Multi-Model Inference, or short M4I approach. And this approach provides one general risk estimate by calculating the weighted mean with weights based on IAC and BIC weights. And so, since we include risk estimates calculated with both weights, we eliminate the question about the best statistical criteria that we should use. So summarizing, we can say that multimodal inference is a statistics information theory-based technique that can be used to assess uncertainty of model choice in, for example, radiation-related cancer risk calculations. However, MMI is associated with greater computational effort, and there are still open questions regarding the stratified baseline problem and the best information criterion to use. Generally, it is recommended to apply MMI in future risk calculations in order to address sources of uncertainties. So at this point, I want to thank Linda Walsh for her support, her help, and her work on this presentation, and I want to thank you for listening.
Thank you. Thank you for providing a new statistical approach to the how to estimate and based on the several risk model and several baseline difference. And okay, do you have some question? The very quick burning question. Okay. Okay, thank you. Shall we next speaker? I'd like to introduce next speaker, Dr. Michael Whale. He's a professor of cancer genetics at Colorado State University, who who studied genetic susceptibilities to radiogenic cancer and space radiation carcinogenesis. He will discuss sex difference in radiation-induced lung cancer risk. Michael, you have the floor for 15 minutes.
Thank you. And I'd like to thank Dr. Wakeford and Dr. Kai for inviting me to participate in this session. So some epidemiological studies show that women are at greater risk for radiation-induced lung cancer than men, but that's not consistent across all studies. So NASA asked ICRP to evaluate the evidence for sex differences in lung cancer risk between men and women, and to recommend approaches for improving lung cancer radiation risk projections. The report that was produced is primarily epidemiology and risk modeling, but it also has sections on animal models and on potential biological mechanisms. These are the members of the committee that put together the report, and I'd like to particularly mention Janice Huff and Michael Story, who contributed to the chapters I'm going to discuss. So first, what do the rodents have to say about this issue? We identified 7 studies in which both male and female rodents were irradiated and in which lung cancer was an outcome. And the results were inconsistent on a sex difference between studies and even within studies. We noted that the lung tumors were not characterized beyond basic histopathology. I want to say that recently that's changed with a very nice paper from National Institutes of Radiological Research at Chiba, showing the importance of the epidermal growth factor receptor pathway in radiation-induced adenocarcinomas in mice. Strain differences in radiosensitivity of the mouse ovary are confounders for applying results in mice to human radiation exposures. I'll show you in a few slides that lung cancers can be estrogen-driven, and estrogen is produced mostly in the ovary. The mouse ovary is ablated at very low radiation doses compared to the human ovary, and consequently, the committee concluded that mice irradiated to the whole body are a poor model for human sex differences. So now we move on to plausible mechanisms for a greater risk in females, and I want to tell you that these mechanisms are not mutually exclusive and may actually interact. So the first one is that radiation exposure could increase risk for a molecular subtype of spontaneous lung cancer that occurs predominantly in women. The second is that differences in sex chromosomes and background gene expressions between men and women might lead to a greater risk in women. Hormonal differences between the sexes, specifically for circulating estrogen, might be a reason for a difference in risk. And finally, sex differences in immune function, which I will not discuss. And a caution here is that none of these mechanisms has been proven. So lung cancer is not a single disease. Until recently, it was classified as small cell lung cancer and non-small cell lung cancer, with non-small cell lung cancer consisting of adenocarcinoma, large cell, and squamous cell. Adenocarcinoma is of particular interest because spontaneous lung adenocarcinomas occur more frequently in females and in non-smokers. So if radiation primarily increases the risk of adenocarcinoma in individuals already at risk for spontaneous adenocarcinoma, it would put females at a greater risk than males. So is there any evidence for that? Yes, some. Among the Japanese atomic bomb survivors, there was a significant excess relative risk at 1 gray for adenocarcinoma in female non-smokers. There's also some genetic data of interest, and this is a genetic association study done by Yoshida at RERF that linked a polymorphism in the epidermal growth factor receptor gene, EGFR, to risk for radiation-induced lung cancer. So we have the following observations. The EGFR pathway is involved in radiation-induced lung cancer, and EGFR mutations are frequent in sporadic lung adenocarcinomas. The EGFR pathway is more commonly used by lung cancers arising in women than in men, and a synthesis of those observations could be that females are at greater risk for radiogenic lung cancer than males due to their greater risk for sporadic lung cancers utilizing the EGFR pathway, specifically adenocarcinomas. So what about differences in sex chromosomes and in gene expression? There are about 60 genes that are differentially expressed in the lung between males and females. Also, in mice, radiation-induced changes in the expression of specific genes in the lung differ between males and females. So perhaps the different gene expression backgrounds could account for a sex difference. What about the sex chromosomes? Well, of course, women have 2 X chromosomes, men have 1. To prevent the genes on the X chromosome from being transcribed at twice the level in females as in males, in each cell in females, 1 copy of the X chromosome is inactivated. That inactivation involves the formation of heterochromatin across about 85% of the inactivated X chromosome and leads to the silencing of transcription from the inactive X chromosome. However, some genes can escape X chromosome inactivation. And this includes a number of cancer-related genes, and within that group of genes, there are 4 genes which are overexpressed in female cells due to escape from X chromosome inactivation that are at higher levels than would be found in male cells. So could escape from X chromosome inactivation lead to an increased risk? Well, one hint on this is Klinefelter syndrome. Klinefelter syndrome are males who have a karyotype of 47XXY. So in each one of their cells, one of the 2 X chromosomes is inactivated as it would be in a female cell. Males with Klinefelter syndrome are at increased risk for adenocarcinomas, or pardon me, for lung cancers. And that's of particular interest because they're at decreased risk for other solid tumors. And we'll skip this one in the interest of time and go to hormonal differences. So estrogen promotes cell proliferation and it's pro-inflammatory. There are estrogen receptors expressed in normal lung and in bronchial epithelial cells. There is some clinical evidence for the role of estrogen in lung cancer. And there are some animal model systems in which estrogen plays a role in lung cancer. But what did not make it into the report, but I think it's interesting and I'll cover it here, is estrogen-driven changes in chromosomal localization within the nuclei. So I'm going to switch now to mammary epithelial cells and look at the induction of intrachromosomal interactions by estrogen signaling. So we'll look at 2 genes which are estrogen responsive, TFF1 on chromosome 21 and GRB1 on chromosome 2. If you look in the interphase nuclei of mammary epithelial cells cultured without estrogen by fluorescence in situ hybridization, you can see that these two genes are distant from one another. However, if you add estrogen to the culture media, within an hour, they co-localize. And not only do the genes co-localize, the territories occupied by their respective chromosomes also co-localize. So here is chromosome 21 and chromosome 2 in cells cultured without estrogen, and the co-localization of those two chromosomes in cells that are cultured in the presence of estrogen. So how can moving chromosomes around in the nucleus contribute perhaps to the risk of radiation-induced cancers? And for this, I'm going to have to switch to another system, which is prostate cancer. About 50% of prostate cancers have an oncogenic fusion gene that consists of the 5' untranslated region of TMPRSS2, which is androgen responsive, and the coding region of ERG, which is an ETS family transcription factor. So if we look at LNCAP cells, and LNCAP cells are androgen responsive, they're a lung cancer cell line, and they don't have the fusion gene. If you look at the position of the two genes, they're separate from one another, or as separate as they can be. They're only 3 million base pairs apart on chromosome 21. In the presence of dihydrotestosterone, so now we're looking at an androgen pathway as opposed to estrogen. In the presence of dihydrotestosterone, those two genes come together. Would that contribute to them forming a fusion oncogene? Well, in the absence of radiation, no, you don't see any clones with the fusion oncogene. With 1 gray, you see about 2% of the clones have the fusion oncogene, and at 3 gray, 25% of the clones have the fusion oncogene. The control here is a different prostate cancer cell line, DUI45, which is not androgen responsive, and despite radiation, you don't see the formation of any of these fusion genes. So a possible synthesis from this would be women with higher levels of circulating estrogen have different territorial localizations of their chromosomes in nuclei of bronchial epithelial cells, which in the presence of radiation can give you oncogenic fusion genes, which would not be generated in men. So a summary here is there are plausible mechanisms that would lead to greater radiogenic lung cancer risk in women than men, but that none of these mechanisms have been proven. And what I haven't told you is there are model systems that would allow some of these mechanisms to be tested. So with that, I would like to acknowledge that the NCRP commentary was funded by NASA. And thank you for your attention.
Thank you. Thank you. He talked about the 4 plausible mechanisms behind the sex difference in lung cancer. Anyways, question, a specific question for clarification? Okay? Okay, shall we move on? Next speaker, I would like introduce next speaker, Sami Erjavi. He's working Canadian Nuclear Safety Commission, and his expertise, radiation science. And he also a member of ICRP Task Group 122, update of detriment calculation for cancer. Sami, you have for over 15 minutes, okay?
So, thank you very much for your audience and for the opportunity to speak today. I appreciate it very much. This paper that we submitted, my colleagues and I, is on a concept study that we're looking on risk communication. So it'll be less technical, but more thought process. The Canadian Nuclear Safety Commission, where we work, is Canada's regulatory body. So we regulate the production and use of nuclear energy and substances in Canada, and we do that in order to protect the health and safety of the public and the environment, but also ensure safety and security. So we have international obligations towards security. And we do that in ways, for instance, with the Advanced Reactor Licensing Division, we issue licenses for reactors, so what you can and cannot do for a given license. In addition to that, we also are required to disseminate objective scientific, technical, and regulatory information to the public concerning those activities. So we need to be the people that answer those questions from the public when they have concerns. And we do that through engagement. And in Canada, one of the biggest things that we respond to is radiation risk. People in the public, as well as Indigenous communities, they want to know not only what dose they're going to get, but how that radiation dose will affect their quality of life, if at all, how it will affect their health, if at all, and also how it will affect their way of life. And way of life is, for instance, if you have contamination environment and if you have an Indigenous community on that environment where that reactor would be built or that storage facility would be built, can they continue doing their traditional activities such as harvesting, fishing, etc. Now, practically what we do is that we have dose limits. So we say, for instance, the public can't get 1 millisievert in excess of 1 millisievert per year, and we can't say the nuclear energy workers can't get more than 20 millisieverts per year. So these are the ICRP recommendations, and they're based on detriment. So that detriment is based on what the ICRP judged to be tolerable. And the CNSC adopted that concept. So this is how we practically implement our RP regulations in the field when we issue a license, that proponents can exceed these requirements. And typically, they are more strict than these requirements. So they make an effort to reduce it even further in accordance with FOLERA. So they try to maintain that compliance very well. Now, detriment as a concept isn't great at communication. It's more of an RP tool. And you can see that it's not an easy concept to understand. It's not everybody can understand the math that's behind it. You can see some of the audience members develop these articles, and some of them are on stage, some of them are in the audience right now, and they had to actually revisit the calculation, and there's a lot of discussion ongoing through TG122 on how to improve detriment. But what's recognized is that we need a better way of communicating detriment. And that's kind of what this paper is about. So when we go to the communities and we say, we're trying to communicate risk to you, what we usually do is we do communicate the doses that they're expected to get for a given scenario. And we try to communicate that they're below regulatory limits. So we say, for instance, you're going to get 0.001 millisieverts per year from this activity. You're below the regulatory limit, and therefore you are safe. And we also might look at different exposure scenarios. We might say this is comparable to an X-ray, it might be comparable to a flight over the sea. It might be comparable, for instance, if you got a CT scan for medical diagnosis. And these presume two things, that A, the audience or the affected parties, they understand that the limits are safe and that they're based on sound judgment. So that's an inherent presumption that we have to make. The other thing that we presume is that if we say that's comparable to other exposure scenarios, that they're okay with that. So those are two big assumptions that we have to make when we do this process, and that's not necessarily effective. That might not be true for that person that we're speaking with. And the other distinction that we have to make is that when we compare it to other exposure scenarios, say, for instance, they got a chest x-ray or they went to a dental x-ray, or for instance, they took a flight across the ocean, that's their choice. If they get an exposure from a reactor facility, it might not be their choice to get exposure. So that distinction has to be clear. And that's something that is not necessarily talked about, that it might be imposed limit versus what they accept voluntarily on their own decision-making. So that's the CNSC regulatory framework. In addition to that, we also have something called the Impact Assessment Act. And this was established in 2019. It's an act by the Parliament of Canada. And it outlines a federal process for conducting environmental reviews, but also assessing the impact on the health, social, and economic conditions of the population that might be at risk from that activity. And you can see that this act is large, it's broad, and involves a lot of groups that need to be communicating with each other to get established. But what's important to note is that they actually adopted the World Health Organization definition of health. So we're not just looking at RP health or radiation safety health, but we're looking at that broader definition of health. And reactor facilities that would fall under this designated act also have to address those. So we're not just looking at RP conditions, But now we're looking at the RP plus the broader definition of health. So how can we improve our regulatory communication using those two acts that we now have to abide by? And is there a better way of communicating risk? From a regulatory perspective, is there a better way of being a regulator in that sense? And this is the concept that we're looking at now. It's a concept study. It's not adopted by the CNSA. I want to make that very clear. But we want to look at disability adjusted life year as an alternative to detriment in communicating risk, but also as a regulatory tool. Now, this is something that's been presented many times before in this conference. We probably had an opportunity to hear Dr. Hiroshi and Dr. Kai's papers presented already. I'll go over those in a sec. So one DALY is equal to 1 health year of life lost. So it's something that we can all relate to. What that means is that we have years lived with disability. So this is, for instance, if you broke a bone, it might take 6 weeks for it to settle. That if that bone was your wrist and it was on your non-writing hand, that might not be a big issue. But if it was on your writing hand, that might be more of a severity for you. It might impact more of your quality of life. So that years lived with disability is supposed to quantify that impact on your quality of life on a day-to-day basis. The years of life lost are if you have an injury or an illness that take away from your expected life expectancy. So this metric is trying to combine those two values into one quantity called DALY. Now, what's interesting is that you can combine or look at all the diseases in a population, and this is what public health does. They combine all these diseases into this one metric, and they get an overall representation of the DALY of a population. And one example is, I took this from the website, IHME, so Institute of Health Metrics and Evaluation. I'm using it as an example of what DALY could look like. This is not an endorsement of IHME, it's just it's easy to show because they did a great job on the representation of what DALY is. And in their paper, they looked at 369 diseases, 204 countries, and I think 80-something risk factors. And they organized those into different categories. So here you can see the DALY for the Canadian population in 2019, averaged over both sexes and all ages. And what you see, I don't know if that shows yet, okay. What you see is that each box represents a different disease. Blue colors represent non-communicable diseases. The reds represent communicable diseases, and the greens represent injuries. So for the top corner, for instance, you'll get heart disease, you might get a stroke, lung cancer, back pain, depression, anxiety. These are all things that impact that population's burden of disease. And you can immediately say from a public health perspective, they can kind of guide the resources to where it's impacting that population the most. Now, if you change it, this picture will change if you go from Canada to Japan, for instance, or it'll change if you go from all ages to a very specific age group. It also changes depending on social development index, economic index, etc. So if you go on the website, you can play around, you'll see how this box changes. And it's different for males and females. Here's just the numbers that are associated with that picture. You can see in Canada, for instance, for males on the left side and females on the right side, that cancers represent the biggest burden of disease on our population for both males and females. But after that, it's different. Like males have more cardiovascular disease, females have more musculoskeletal disorders. And that ranking goes down. And you can see the contributions from years life lost to and years lived with disability. If we look at cancers, this is, we talked about this now, you can see that there's different cancers and that lung cancers represent the predominant cancers in Canada. So neoplasms, if you broke that down, this is what that would look like. And you can see it goes all the way down 25 disease categories. What's interesting is that the risk factors for those are listed here. So you have tobacco use, alcohol use, dietary risks, lifestyle issues, occupational exposures, environmental risks, metabolic risks. These are all factors that contribute to your burden disease. Radon exposure is the only instance that they have for exposure to radiation as a contribution to these disease risks. They don't include artificial risk exposure. And that's what we'll get to in a sec. Dr. Kai in 2015, this is what brought me to this conference and how I got to meet him, and Dr. Hiroshi as well, just now. They presented a paper on how to calculate excess risk of DALY from radiation exposure. And they did the math and they showed the methodology, et cetera. And I won't go into that, but what they showed is that it's doable to say, if you have an radiation exposure, how does it contribute to your overall DALI? So now we have the opportunity to merge radiation exposure with something that's already widely used in public health towards decision making. And as a regulator, that's important. Now we can answer a lot of the questions that we're supposed to answer or we're supposed to be responsible for from a regulatory perspective. Remember, we have the IAEA definition of health, the World Health Organization definition of health that's adopted by the IAEA, and also the RP concerns that we're interested in. So what's the benefit? Why is DALI versus detriment? Detriment is still useful. It's not that we're trying to replace it, but DALI might be a better way of communicating those same risks to the affected parties that are interested. This is more, it's a more easier concept to understand than detriment. And it's more widely used, so it has more users than detriment. So if you go to public health, if you go to medical professionals, people deciding on clinical treatments, people in emergency management, they can use DALI. It's easier to communicate. They can have a sense of how to adopt different policies more than what we'd give them with just detriment. So as a regulator, we can apply ourselves to detriment as opposed to staying siloed in our own environment. For a local population, DALI can be tailored. So we can look at that community in and around the region of a reactor facility. We can say, we can calculate your DALI for that local population. We can understand your specific risks, your lifestyle risks, metabolic risks, environmental risks. And we can say, here's your baseline and here's how certain radiation exposure might impact it. We can do this as a function of sex. We can also do it as a function of years life lost versus years lived with disability. We can give people a sense of how it will impact your quality of life. And as I said, it's easier to communicate. 1 year of healthy life lost for everybody, I believe, is probably easier to understand than the 2% increase in excess lung cancer, for instance. This is something that we can just verbalize easier. It's also something that Task Group 122 is looking at. So you can see here one of the goals of Task Group 122, led by Dr. Vaillant and Dr. Wakeford, that they're looking at ways of improving detriment using concepts taken from DALI. So it's not such a novel idea that's already being looked at in ICRP, but it's something that we might look at from a regulator's perspective as well. So how does that look like practically? Well, for instance, here's cancer or neoplasms, the risk factors for neoplasms. You can see, for instance, that smoking is responsible for most of the cancers. Then it's followed by high body mass index, alcohol use, occupational asbestos, etc. You can see radon is down here. What if you included artificial exposure to radiation as one of those risk factors? It's just one risk factor among many that people deal with on a day-to-day basis. We shouldn't be treating it as more severe or less severe. We should just be treating it as one risk factor of many that population will have to deal with on a day-to-day basis. If we look at the overall picture, 80% of the total burden disease is in years lived with disability. We're only looking at 20% cancers. The rest of it is other diseases. What if, for instance, down the line, it was decided that radiation exposure increases cardiovascular disease or does impact the generation of cataracts, for instance? How would that impact the quality of life of those people? And the flip side, if you're a proponent and you submit an application and you want to say, I want to build a reactor, how would that improve their life? Would it reduce environmental risk factors? Would that take away from respiratory illnesses? Would it improve education? Would that improve healthcare, infrastructure? And these are all risk factors that contribute, for instance, to falls and injuries or road accidents. So can we do an optimization? Can we reduce your overall DALI from a given project while also looking at the risk factors and trying to put that in perspective? And as I mentioned, it also aligns with our current infrastructure or regulatory infrastructure in Canada. We have to abide by the Impact Assessment Act. We also have to abide by the Nuclear Safety Control Act. And then finally, what about emergencies? If we have a baseline DALI for that population, and in case of emergency, we can plan in advance, how would that look like? What would we do to best address that emergency? Would we evacuate? Would we not? How would we devote resources to mental anxiety or change in lifestyle, change in diet, etc.? These are all things that came out of, for instance, a study that you can see here that they listed, that the recovery phase is important. And DALI, as a concept, can be used to address that recovery phase, but also can be used to address the decision-making during an emergency. So from a regulatory perspective, these are things that we consider in advance of granting a license. We say, what happens in case of emergency? What would you do? How would that look like? What would the exposure scenarios be? We're doing this already, but now we have a tool that we might be able to address different scenarios. So this is not straightforward. It's going to be a lot of work, and you can see some of the challenges ahead. There's a lot of similar challenges to what's being dealt with when you're trying to do excess risk calculations or lifespan studies, et cetera. We're using a lot of the same data sets though. So that's important. We're not using different data sets than what already being there, and we're not using different methodologies, but we're applying them, we're merging them together. And the last thing that we have to keep in mind is that we still have this challenge of taking all that data and using the best communication practices to communicate and address the concerns that people have come with. But now we have more information or more ways of representing that risk. So thank you very much for your time. And if you have any questions, please reach out.
Thank you. Thank you very much, Sami. He talked about how to improve the communication with the public, and he also focused on the risk indicator, DARI. Okay, do you have some question about the burning question for clarification? Okay, please.
Yes, thank you very much for the talks. I have a question for Michael Weiss. Do we have evidence of or explanation of the difference between male and females for other types of cancers than the one you presented for lung cancers?
Okay, so it does seem to be working. Well, yeah, and this will seem to be a very glib answer. You know, obviously ovarian cancer only occurs in women. But for some of the other tumor types, you know, I could give you a list of mechanisms that would put males at greater risk. And I could probably do that for lung cancer. So I would take this as being extremely ephemeral. We don't have any solid data that says, oh yes, this is the mechanism involved, at least in lung cancer.
Okay, shall we move on? General discussion time, and Dr. Record chair the general discussion time, please. Okay.
Thanks. So, wide-ranging papers for sure. Questions from the audience for any of the speakers at the moment? Oh, there you go. Please.
Mahesh, question is for the last speaker about the concept of DALI. I like it, but my question to you is, what unit do you retire to maintain status quo of not introducing new units to the radiation discussion? Number one. Number two is, if you look at the DALI value for the population and with and without radiation exposure, and if the DALI risk is so small, it does not change much, are you not worried about a government agency adding more fund for any radiation protection studies?
More funds, you said?
What I meant is, like, they will say, look at your unit DALI,
Yes.
with and without radiation exposure to the population, and it did not change much. So why do you need fund to study further on radiation risk assessment?
So well, personally, I think if they direct the money where it makes the most benefit, that's the best answer I can give you.
Okay.
If it's not radiation protection, I'm happy with that. It doesn't take away from my...
Okay. The earlier question is, like, we have been used to the effective dose or all those so many units.
Yes.
If you introduce DALI, which unit do you want to take it out from the discussion?
So DALI is not meant to replace other units. I think from this perspective, you need those other units. You need radiation protection units. You need affected dose, quality factors. You need excess risk. You need all those models because it'll inform DALI.
Understand.
DALI is the link between what we talk about and what the audience wants to hear, in my opinion.
Understand, because the ICRP is encouraging to minimize units.
Yes.
Not to confuse the population. So you already have so many units, and now you're adding DALI in.
So DALI, again, I think think of it this way. It's if you're trying to speak only in radiation units, the audience, the broader audience, public health officials, government officials, etc., they cannot speak to you because they don't understand that unit. There's a gap in communication. I think that's the problem I'm seeing. I guess I heard in this conference is that justification, tolerability, communication, stakeholder engagement, decision making, these are all things that need to be considered. But right now, if we're speaking to ourselves, you cannot consider it because we're not the decision makers. We only give you the science. The decision makers have to give the policy. And
I agree because I like your unit. DALI is very nice. But my question is, do we need to retire any other one so that we don't confuse it? That's why.
no,
Thank you.
I don't think so. I think you keep the units because they're important for the science.
Yeah, I mean, recent ICRP publications have pointed to weaknesses in the severity weighting that are used to go from risk coefficients to detriment. Well, to me, it's reasonably clear that we've got to go, beyond this. I mean, as I say, these weaknesses have been pointed out. So really, we're looking at ways, and DALI is obviously one of them, to overcome the weaknesses of the current severity weighting system that is used in publication 103. But that doesn't necessarily mean to say that we have to get rid of effective dose. It's just a different way. And of course, we move all the time from how we define effective dose because we change the weighting factors. So, I mean, task group 122 is actually, looking specifically at this particular issue. Yes, that's Abel, I can see, and I can see another hand as well. So Abel first.
Thank you, Richard. I have a question to Luana to this very interesting paper on multimodal. I noticed that when you compare your result with other studies, the normal epidemiological studies, the biggest difference is with the in-work study. This is what I noticed in the slide. Now, your reference there is to the old in-work. And as you know, a few weeks ago, there was a new paper on in-work where there is much big difference with the previous one. Therefore, I presume that the difference now will be bigger. Is correct?
Have you got it, Lorena? Or would you
I'm
want
not
to
sure whether I understood the question correctly.
Can you just
So-
clarify that again?
So you're asking whether inworks is included in?
Yeah, I ask you refer to the difference between the multi-model studies.
Yes, exactly.
And other
studies.
And I noticed in the slide, probably so wrongly, that the biggest difference was with the in-work study. But the reference that you put there is the old in-work.
Mm-hmm.
Now, the new in-work report that was a few weeks ago is substantively different than the old one. Therefore, the difference will be bigger now.
This could be, if you don't have performed MMI with the inworks included, so I can't really tell what the result will be. That's...
Okay, there's one here and there's one there. That's first.
If you have to do an exercise for correlating the liability or the compensation to any criminal activities using radioactive sources or transboundary release condition, how we can go about it? Any suggestion? Liability or compensation due to radiation exposure following criminal activities using radioactive sources or due to negligence, a transboundary release situation. Thank you.
Is this to anyone in particular? Is it Sami?
Pardon?
To anyone in particular, or?
No, any. Maybe more relevant to the earlier one, but earlier speaker, or if anybody responds, because I'm interested to know, because now we talk about nuclear security events and so many. So if we have to do this exercise, how we can go about it?
If we had to quantify monetary damage, liabilities, et cetera, I guess that's what you're asking? Monetary damage in case of an accident, in case of a malicious event, how do you quantify the liabilities? How do you quantify the punishment, I guess? Is that the question?
But ultimately, you will be calculating the average life lost based upon the exposure to the group of people or individual, or how do we go about it?
So I can say in Canada, we do not do that. That's not for me to answer. But I would say that when you talk about radiation exposure and you talk about detriment, you already, like if you talk to Dr. Brenner, you can model years life lost, you can model all these numbers anyway. What DALI, if you're specifically referring to DALI, is it's just a different way of looking at that same data set, same number, same excess risk. So we're not changing the numbers, we're not changing what we have, we're just putting it in a different framework. I can't speak to liabilities. As a regulator, that's not my scope, so I will not answer that question because I just don't know the answer to that one. And I'll pass it on to my colleagues maybe that they want to answer.
Thank you.
Please, yes.
Hello, thank you very much for your talks. I also have a question regarding DALI, not to do with the allocation of resources, but rather on an individual basis. So when using it for, you say, to increase effective communication, my question is, have you seen this become more effective? How do you determine that communication has become more effective? What are the key success factors? Have you seen changes in decision-making based by the user or by the person exposed, I guess I would say? Yes, could you expand on that, please?
So I want to emphasize this is not something that we do in practice right now. It's an idea that we're looking at. From my understanding, and I'll leave it to the physicians in the audience, that when they have discussions with their patients, they do this type of analysis using other factors, other similar metrics like quality adjusted life year or healthy adjusted life year. I think I even heard of a happy life year in this conference. They use that to judge the quality of treatment, and they have that conversation with their patients. So I can imagine if we have that conversation with our communities, and it necessarily has to be with the communities, because those numbers will represent the communities, not all of Canada. They'll represent that local community, for instance. Mm-hmm. We can have that conversation. We can understand what's impacting their life as it is, and then we can start having that discussion of if we put this facility near you, if we have this type of accident, if we put this other object in your area, we can have that conversation. How will it impact your life? And that's the discussion that, as a regulator, we can start having if we have the numbers, but also they can now communicate with other officials, like the physicians, the emergency responders, the government officials, the proponents, the people who want to put that object in there. They can have that discussion, and we can all talk using the same language. And I think that's the key. We can talk using the same language. Right now, we do not talk with the same language.
Okay, perhaps to clarify my question, how do you deem successfulness then at the end of this?
From
a regulator point of view?
I think when we issue a license, if we ever get to that point, we have to satisfy the need to communicate, to satisfy the need to engage. Not everybody's going to be happy, but if we can address most concerns and people feel that they had their concerns addressed, that's success.
Okay.
And then whoever decides whether or not to grant the license, they will take all that information and decide, did we meet that expectation, yes or no? And if we did not, no license will be issued. If we did, then chances are they'll probably issue a license.
Okay, thank you very much.
Oh.
Okay, thanks. There's Dominique over here.
Yeah, thank you, Richard. It's not a question, it's just to give you an answer to the point raised by Abel just before. Yes, InWorks is a very big study of nuclear workers, but the new results that have been published are just an extension, an update of the previous results. And the new results on the whole cohort are completely coherent with what has been published before, but the increase in the statistical power reduced the confidence interval. So the question was, will it change the results compared to what you presented? As the whole cohort, the model from the whole cohort was concerned, clearly it's not going to change at all. But the new results provide the information, provides better information to look at the low dose range. And the changes are in the low dose range. But to answer your question, Abel, clearly using the new data in the analysis that you have used will not change dramatically the results. And I fully agree that if we want to have the global picture, we have to look at all the studies. INWORKS is one study, but it's important to put it together in the context of all the available data.
Okay, thanks. Any comment? No. Okay, thank you. So, have we got any further questions, or are we going to call it a day there? No one else? Okay, and you've got a point to make. Yeah.
Sorry, my observation of the diary at one point. It's okay. Yes, okay. Yeah, diary is characterized by the not probability this unit, but diary expressing year, health last year. This is a point, and I think because it's very easy to communicate to the public. If you talk about the probabilities, this is not easy to communicate with the meaning, but the diary is other field and public health and environment protection, and it is very widely used, and this is the point. Thank you. Okay. Oh, sorry.
Just one point I forgot to mention. Dr. Kai just touched on it. If, as a community, we're trying to bring consensus to how we approach radiation protection, DALI, the framework, can be adopted by many people. The inputs will change, the results will change, but the methodology will be the same. And then now we can start saying, okay, if we transplant myself to Japan or vice versa, can we speak the same language? And I think that's important because it's widely used. Right now, risk models are not widely used between countries. Everybody has their different models. Some people adopt different other models versus another one. And that it might be possible with DALI, if it's already widely used, that we can adopt the same models. And that's another benefit to DALI.
Thank you. Thank you very much. We close this session.